Hello and welcome to a lesson on solving linear systems algebraically. So in our previous topic, we talked about what it means to have a system. We're looking at two or more equations considered at the same time. And we said that the solution to a linear system, that is two equations, two variables, both those variables are to the first power, that we could just graph the two lines in the system and find the point where the lines cross. That point would be the solution that they share, the solution they have in common, and therefore the solution to the system. Now there are other ways to solve. The algebraic ways to solve is what we're going to look at today, because we don't always have access to technology, and we should be able to do some of these things by hand. This is an algebra class, let's do some algebra, right? So one of the ways we can solve algebraically is using substitution. Now, if you're solving algebraically, this is the method that's going to be preferred when at least one of the variables is alone. So one of the variables is isolated, meaning at least one of your equations is y equals, or at least one of your equations is x equals. So we want a variable all by itself on one side of that equation. If we're going to use this method, that is preferred. And the goal is going to be to basically use substitution is to substitute in one variable, or to get one equation with one variable using substitution, okay? And I'm going to show you how that works. But let me give you some steps and then I'll walk you through how to use them. So if you don't already have a variable alone, and ideally you would, then you would pick one to get alone. And so you can solve one of your equations for one of the variables if you don't have that situation already. And the variable that you choose to get alone is going to get replaced in the second equation. So you're going to substitute, right? Replace x in for whatever x, or replace x with whatever x equals, or you're going to replace y with whatever y equals. So the variable that you get alone is going to get replaced. And again, I'll show you this when we work through our examples, okay? When you do that, that's going to leave you one equation with one variable instead of two equations with two variables. And then you're going to solve by getting that one variable all by itself. And that's going to produce half of your solution, right? You're either going to have your x value or your y value, and then you'll just plug that back in to find the other half. And then just remember, the solution is a point where our lines cross, so we want to make sure we write that solution as a point with the x value and then the y value. Okay, so here's what I'm trying to say. You want one of your variables to be alone, and we have that here. We have y all by itself. So since y is alone, I don't have to actually choose a variable to get alone. But since y is by itself, then y is going to be replaced in the other equation. If we know y is equal to, right, it's equal to 6 minus x, then we can replace y in our first equation with what it equals, which is 6 minus x. So our first equation we can rewrite as 3x minus, instead of y, we can substitute in what it equals, which again is 6 minus x. And then it's going to equal a negative 10. So in our first equation, the y gets replaced with 6 minus x. But the rest of the equation, notice, is the same, right? We still have a 3x and a minus, and we still have an equals negative 10. We just replaced y with 6 minus x. And now, instead of two equations, two variables, I have one equation, one variable. So this is going to allow us to solve for part of our solution. So this is 3x. If we distribute here, we get a minus 6 and then a plus x equal to negative 10. Combining like terms here, I have 4x minus 6 equal to negative 10. And now I can add 6 to both sides, and that leaves me 4x equals negative 4. And now I can divide both sides by 4, and again that gives me part of my solution. I can see now that x is going to equal negative 1. So that's part of the solution, right? That's the x value in the point where these lines cross. Now I want to find the y value by plugging that x value in. Now it doesn't matter which equation you plug into, but it's generally going to be the one that's already got a variable by itself. So in this case, I'm going to use the second equation. The second equation says y is going to equal 6 minus x, which we just found was a negative 1. So y is going to equal 6 plus 1, which makes it 7. So our solution our solution is going to be at -1, 7. Okay, that is the point where these two lines will cross. Now again, we have technology, so we might as well use it to confirm what we're doing here. What we're saying here with this algebraic process is if we graphed a line, 3x minus y equal to -10, and we graphed a line y equals 6 minus x, that these two lines would cross at -1, 7, and in fact they do. Okay, so you can use technology to verify. Remember, you can also verify by plugging that point into both equations and making sure that you get a true statement. Okay, so lots of ways to check your work. All right, so number 2, we want to pick a variable to get a lone, but we already have that here. We already know x is all by itself and that x is equal to 3y minus 4. So if x is equal to 3y minus 4, I can replace x with 3y minus 4. So the variable that's alone gets replaced. So I'm going to take this 3y minus 4 and I'm going to plug it into the other equation for x, right? So my first equation, instead of being 4 times x, becomes 4 times what x is equal to, which is 3y minus 4. So 4 times, instead of x, 3y minus 4, and then we have a minus 5y and an equals and a -2. So again, it's just so you can see what we're doing here. X gets replaced with what it's equal to, so that's where the 3y minus 4 came from. The rest of the equation is not changing. I still have a 4 in front, I still have a minus 5y, I still have an equal to -2. Okay, so I'm just replacing the one variable with what it's equal to. But now, instead of 2 equations, 2 variables, it's 1 equation, 1 variable. So just, oops, let's turn the pen back on. Distributing, I have 12y here, minus 16, minus 5y equals -2. Combining like terms, 12 minus 5 is going to leave me 7y, minus 16 equals -2. And now if I add 16 to both sides, I see that 7y has to equal 14, and now dividing both sides by 7, I can see that my y value in my solution is going to be 2. Now that's just part of the solution. I still have to plug that in to find the other part, and again I'm going to plug it in right to the second equation here, so I know x has to equal 3 times y, which we just found was 2, minus 4. So that's going to be 6 minus 4, which makes my x value 2. So this system has a solution at x equals 2 and y equals 2. So at 2, 2. That's, if we were to graph these two lines, that is the point where these two lines would cross. Okay, so I have one here. I think this would be a good opportunity for you to try and make sure that you know how to do this process. So if you're feeling up to it, pause the video and give it a shot. If not, let's do this together. So y is all by itself here in my first equation. If y is equal to x minus 4, then I can replace y with x minus 4. So my second equation becomes, instead of y, it becomes x minus 4 minus 2x equal to -8. So again, I replaced y with what it equals, so that's where the x minus 4 comes from, and then I am not changing the rest of the equation, the minus 2x equal to -8, still there. Okay, but now again, instead of 2 equations, 2 variables, it's 1 equation, 1 variable. So I have x minus 4 minus 2x equal to -8. If I combine these like terms, I have -x minus 4 equal to -8. I'm going to add that 4 over. So I have -x equal to -4. And then lastly, I'll divide both sides by -1, which tells me x has to be positive 4. So there's the first part of my solution. Now I'm going to plug back in to, again, my first equation so I can figure out what the y value is in my solution. And so y has to equal x, which we just found was 4, minus 4. Well, 4 minus 4 is 0. That means that this system has a solution at x equals 4 and y equals 0. If I was to graph these two lines, that is the point where the two lines would cross. Okay? So that's a process called substitution. Again, that's a process that is ideal when you already have a variable all by itself. If you have this situation where it wouldn't be too hard to, let's say, get a variable alone here or here. You know, if I wanted to take y and get it by itself, I could just subtract the 3x over and use substitution. That's totally fine. But when your equations are both in standard form, there is another option that works quite well. And the reason we want the option is not so much for a system like this one, where getting y alone, for instance, wasn't too bad. It's more for a system like this one. If I wanted to choose to get, let's say, this x by itself, well, I would have to subtract over the 6y, and I would have to divide by 4. And then I would be plugging in something with fractions into the next equation, and I don't know that I want to do that. And the same would be true if I wanted to get y by itself here, or y by itself here, or x by itself here. So getting a variable alone is not always ideal, which is why we have this other process. We call it elimination. It's also sometimes referred to as the addition method. And you're going to see why in just a second. So elimination is also called the addition method. And what we're doing here, again, is if we're solving algebraically, this is going to be the method preferred when both of your equations are in standard form. That's where your x's and y's are all lined up, right? Ax plus by equals c for both of them. So the x's are lined up, the y's are lined up, the constants are all lined up. Everything is aligned. That's the goal. Or that's the preferred setup if we're going to use elimination or the addition method. And the goal for this method is to actually add the equations together to eliminate a variable, which sounds crazy, but we're allowed to do this. Just don't write this for a second, but let's say I solved an equation and I got a solution of x equals 2, okay? And let's say I solved a separate equation and I got a solution of x equals 2. Now if I added these two equations together, 1x and 1x would be 2x, and then 2 plus 2 would be 4. Well, what's the solution to this new equation? Well, if I divide both sides by 2, it's still x equal to 2, right? Adding equations together does not change the solution. So this is going to be a method that's really helpful here. All right, now what we want to do is choose a variable to eliminate, and you're going to choose wisely. Again, after I give you these steps, I'll show you how to use them. What we need in order for this elimination to work is for the coefficients of the variable we're eliminating to be opposites. So for example, in number 3, I would choose to eliminate y's here because my coefficients are already opposites. If I add this to equation, add these equations together as is, these would already cancel. A positive y and a negative y go away, and we would be left with 8x equal to 16 on the other side. That's exactly what we want in this situation. We need, for whatever variable we're trying to get rid of, we need their coefficients to be opposites, okay? Like a positive 1 and a negative 1, or here, like a positive 6 and a negative 6. So we want the coefficients of that variable. They must be the same number with opposite signs. Like 3x and negative 3x, 1x and negative 1x, 6y and negative 6y. And it's possible that you have to multiply to make that happen. I'll show you that in just a little bit. And once we have that, and sometimes we start with that, we will add the equations together. That's a legal move. And again, what that's going to do is the same thing substitution did for us. It's going to leave us with one equation with one variable. And we solve it to get part of our solution, and then we plug that in to get the other part of the solution. Okay? So for example, again on number 3, if we add these equations together as is, y's are going to cancel. Positive and negative 1 cancel. We're left with 5x and 3x, which is 8x, equal to 4 plus 12, which is 16. And then dividing both sides by 8 here, we have already half of our solution. I know that the x value in the solution is going to be 2. So now I got to plug it back in, and here it doesn't matter which one we plug into, so I just typically choose the first equation, but it doesn't matter. So I'm going to plug 2 into the first equation. 5 times 2 minus y has to equal 4. So 10 minus y has to equal 4. And if I subtract over the 10, I can see that negative y has to equal negative 6, which means y has to be positive 6. So the y value in my solution is positive 6. So this system has a solution at x equals 2 and y equals 6. And again, if we wanted to verify, we could graph those two lines and see that that's the point where they cross, or I could plug 2, 6 into both equations to verify I have true statements resulting. Okay? So here's another one. I think because this is set up perfectly for us, it'd be a good opportunity again for you to try the process. If not, let's do this together. So again, we can add these as is. I would choose to eliminate the y's here because adding these as is, positive 6 and negative 6 will cancel. So we're left with 4 plus 5, which is 9x, equal to 24 and 3, which is 27. And then dividing by 9 here is going to give me the first part of my solution. I can see x has to equal 3. So now if I plug that in, again, I'm just going to choose to plug into my first equation. 4 times x, which is 3, plus 6y has to equal 24. So 12 plus 6y has to equal 24. If I subtract that 12 over, then 6y has to equal 12. And dividing by 6, I can see y has to equal 2. So this system has a solution at 3 and 2. 3 and 2. So again, if you were to graph these two lines, you're going to see that is the point where these two lines would cross. Okay? And looking at number 4, this is a little different. Okay? If I tried to add these equations together as is, I would have 8x's here, and I would have 5y's here, and I would have negative 18 here, and that's no good. I just created a third equation that still has two variables in it. The point to adding the equations together, which is still doable here, but the point is to get one of the variables to go away. And so what we're allowed to do is we're allowed to multiply an equation. It's like, again, if you had x equals 2 as a solution to your equation, let's just say you multiplied the whole equation by 4. That would give you 4x equal to 8. Have you changed your equation? No, because if you divide both sides by 4, you still have the same solution of 2. So we are allowed to multiply an equation by a number, just like as long as we do it to both sides, just like in the solving process. If I add 2 to both sides, if I divide 4 on both sides, if I multiply 4 on both sides, this is a legal thing. It keeps the balance of the equation. So we want to choose a variable to get rid of. And it doesn't matter which one you choose, but what you're going to be trying to establish is a least common multiple for their coefficients. So for example, if I choose to eliminate the x's, I need for these coefficients to be the same number with opposite signs. So what I'm going to look for is the least common multiple for those two numbers. So what's the smallest number that 2 and 10 both divide into is going to be 10. Okay, so if the least common multiple is 10, that means I want one of my coefficients to be a positive 10. I want the other coefficient to be a negative 10. Well, one of them is already a positive 10. So the only thing I would have to do is take the second equation and multiply it by 5 to make the other one the negative 10. Okay, now I would have to multiply the whole equation, but you can see I would only have to multiply one equation. Now, if we look at the y's, the coefficients here being 4 and 9, the least common multiple for 4 and 9 is 36. It's like when you're looking for a common denominator, okay? The smallest number that 4 and 9 both divide into is 36. So that means I would have to multiply both of these equations to make one of those coefficients a negative 36 and the other one a positive 36. So maybe multiplying here by 9 and then multiplying here by 4. So again, negative 36 and positive 36, that way those would cancel. Now, I don't want to have to multiply two equations when it's possible to fix this by multiplying just one. So that's why up here, when I said choose a variable to eliminate, when I said choose wisely, okay, which one is going to be less work? In this case is going to be x. So here, again, the least common multiple for 10 and 2 is 10. So I need a positive 10 and a negative 10. Now I already have a positive 10 in front of the first x, and I can make this a negative 10 by multiplying this entire equation by 5. And so my system, this is not going to change. I'm going to leave the 10x, the minus 4y, and the equals negative 2. But the second equation, multiplied by 5, becomes a negative 10x and a 45y equal to, this is a negative 80. Okay, so now my system is going to work. Now, when I add these two equations together, the x's will cancel, which is exactly why I did that. 45 minus 4 leaves me with 41y, and negative 2 and negative 80 is a negative 82. So now dividing both sides by 41, I see the first half of my solution, that the y value in my solution is going to be a negative 2. Now I'm going to plug that in to get the other part of my solution. It doesn't matter which equation we plug into. It could be the first one, the second one, the third one over here that we just got. I'm going to go ahead and just plug into the first one. The first one says that 10 times x minus, I can't read that, yep, minus 4 times y, which we just found was negative 2, has to equal negative 2. So that's going to be a positive 8. So 10x plus 8 equals negative 2. If we subtract that over, then we can see 10x is going to equal negative 10. And then lastly, we can divide. And so we see the x value in our solution is going to be negative 1. So the solution to this system is going to be at negative 1 and negative 2. X equals negative 1, y equals negative 2. And again, that can be confirmed by plugging that solution into both equations or by graphing to see that that is the point where these lines cross. Okay? So if you want to try the next one, I know that's a tougher process, give it a shot. If not, let's talk this through here. So if I want to eliminate x's, the least common multiple for 2 and 7 is 14. So I would have to maybe multiply this one by 7 and multiply this one by negative 2. And I don't know that I want to multiply both equations if that's not necessary. So that would take, again, multiplying here and multiplying here. And I'm just choosing to put the negative with the 2. If you wanted to multiply by negative 7 here and positive 2 here, as long as you get a positive and negative of the same number, it's going to be fine. Now if I want to multiply, or if I'm going to eliminate y's, the least common multiple for 2 and 4 is 4. So I already have a negative 4 here. If I just multiply by 2 here, I can get the positive 4, and that's less work. So I'm going to choose to eliminate the y's in this one. And I'm going to do that by multiplying this first equation by a positive 2. So my system becomes, this is going to be 4x plus 4y, 4x plus 4y equal to 24. And then I'm not changing my second equation, it's just coming over. 7x minus 4y equals negative 2. And now when I put these together, those y's cancel out, which was exactly the goal. So 4 and 7 is 11x equal to 24 minus 2 is going to be 22. Dividing both sides by 11, I can see the x value in my solution has to be a positive 2. Now I'm going to plug that in, and I'm going to go into the first equation. 2 times x, which we just found was 2, plus 2 times y has to equal 12. So 2 times 2 is 4. If we subtract that 4 over, then we see that 2 times y is going to equal 8. And if we divide that over, then we get the other part of our solution. So we see y has to equal 4. So the solution to this system is going to be at x equals 2 and y equals 4. And again, you can confirm by plugging in or graphing to see that that is the point where those lines cross. Okay? So that's the algebraic options for solving systems, but by all means use your technology to confirm your work. Now this is absolutely a skill that you need, so even though you can use technology every time, please practice this skill. So work on those practice problems, and as always, if you need some extra help, then just reach out. Alright guys, take care.